Solving simultaneous equations with quadratics is very similar to linear simultaneous equations. There's just a bit of more process because we have quadratic equations, so that takes a little bit longer to solve for. But in general, the process is exactly the same. And a lot of people kind of get confused by this because they see these complex equations and they might think that the process is exponentially more complicated, where it's actually not. What we have is y is equal to something and y is equal to something else, so we just use our traditional process of substituting y for y, or just letting equation 1 equal equation 2. So we'll say equation 1 is equal to equation 2. So what we end up getting is x squared minus 5x plus 6 is equal to 3x minus 6. So then what we do is we move everything to one side and then we get 0 on one side. This is kind of different compared to linear equations, because for linear equations, we just go directly to isolating x, because we'll have some x terms, so we combine the like terms, and then we'll have some constant terms, so we'll leave them on the other side, and then we just rearrange our equation for x. But in this case, it's slightly different. Just in general, solving quadratic equations is different, so we have to just replicate that same process in this case as well, because if we wanted to solve for our x-intercepts of an equation, then we need to make sure that everything's on one side. The only thing is, we don't really think about that usually, because everything is usually on one side. We have y is equal to our equation, x squared minus 5x plus 6, like this one here. So if you wanted to solve the x-intercepts hypothetically, you don't have to do anything. We just have to equal 0, and then you factorize. In this case, it's exactly the same. We want to factorize, but in order to factorize and use the null factor law, we need everything on one side, and we need to have 0 on the other side. So in this case, what we do is we move the 3x to this side by minusing it, and then we move the 6 to the other side by adding it. So we end up getting x squared minus 8x plus 12 is equal to 0. And then this is our kind of root finding equation, we kind of think of it as. That's what we call it in engineering, but you kind of just think of this as the equation we need to solve for in order to get our x-intercepts or x solutions for the intersections between these two equations. Even though this looks like solving for the x-intercepts, it's actually not. This is just the equation that we use to get there, or the means that we use to get there. So in this case, what this would be is x minus 6, x minus 2 as a factorized form is equal to 0. Therefore, we end up getting x is equal to 6 or 2. So we have two intersections in this case. We could have one, and we could have none as well for quadratic equations. And when we talk about the determinant in the future part of this course, we talk about how to determine how many solutions there actually are without actually solving our equation. In this case, we can see that we have two solutions, so obviously we just have two, and then we can find those intersections. Now we just substitute it into either one of our equations. Simultaneous equations, it doesn't matter which one you substitute it in. I'm going to substitute it into 2 because it's a lot easier. So x is equal to 6 in equation 2. What we get is y is equal to 3 multiplied by 6, which is 18, minus 6, which is 12. And then for the 2, y is equal to 3 multiplied by 2, which is 6, minus 6, which is equal to 0. So we have two intersections in this case. We have 6, 12, and we also have 2, 0. So now what we can do is represent this on a graph. X squared minus 5x plus 6, that is the same as x minus 3, x minus 2. So that's going to have x-intercepts at 3 and 2. So 2 would be roughly there, 3 would be there. Yep, good enough. And then we just sketch this like that. It should be pretty low. The turning point should remain close to the x-axis. I'm not going to get all the information here because it's not really that relevant for this question. And then we have 3x minus 6, which would look something like this. And I can see we're intersecting through the x-intercept. So I'm just going to keep that in mind when I'm sketching. So I want to make sure that the graph actually passes through that point there and then intersects somewhere later. So one of our intersections we found was 2, 0. One of the other intersections that we found was 6, 12. Cool, so this would be the graphical representation of two intersections between equations. Let's just imagine what 1 and 0 intersections would look like. If we had a linear equation that had one intersection, what that would look like is a graph that is tangent to the curve. So a linear equation might look something like that, where we have one intersection because the linear line just scrapes against the parabolic curve. This is a possibility, but it's a pretty rare possibility. But it is possible, so it could be a situation that you're actually looking for. And it just has to be a perfect sequence of events. Obviously, you have to have a perfect line that just scrapes against the curve and doesn't completely cut through like this blue one does. The other pretty common case, it's probably equally as common as two intersections, it's just the fact that you have no intersections. So if your linear equation completely misses your parabolic equation, then obviously you'll have no solutions or no intersections in this case because you can graphically see that those two functions never meet.